Welcome to Complexity Made Simple. My name is Paul Allen, and before we get into today's video, we've got a fantastic announcement about the latest online Yellow Belt course that we've just released. If you go below this video, you will see the link that will take you straight to that Yellow Belt course, and it will also give you access to a 24-hour limited discount offer on the price of this course. This material contains all the techniques that I use 90% of the time with my clients. If you want to start to become a world-class technical problem solver, this isn't just a certificate, this is world-class skills buried in this course, then this is the course for you. We are delivering some of the best skills online anywhere in the world. Click on the link, get the best Yellow Belt course you'll ever see right now. Okay, so now we're going to take a look at a continuous distribution, the normal distribution. And of course, this is often one of the most common data sets that you create, the normal. Anytime you measure anything, if you measure a dimension, you measure a weight, that type of thing, you measure volts, lumens, anything that you measure, you're typically going to create the normal. Not every time, but I would say 95% of the time you're going to create a normal distribution. Now the parameters in this case we are fairly familiar with, so we need parameters of course when we look at a probability distribution. The parameters we're familiar with: the signal, which is the mean, and the standard deviation, which of course is the noise. So there are the two parameters. And then of course, what's the question that we're normally going to answer? Well, it's normally a defect rate. So we'll take a look at one of those examples in a moment. So normally, how does the normal distribution show itself in your organization? Well, you measure something, and of course then you compare it to two tolerances, an upper and a lower tolerance, and you're normally interested in the question: how much data falls below the bottom tolerance, how much data falls above the top tolerance. Now, if you use observation, you're likely to underestimate the defect rate. So we tend to get our estimate of the defect rate from the normal distribution, often using CPK, of course. So let's take a look at an example. We'll get some parameters and we'll get the question up. Of course, the nice thing about this distribution, unlike the discrete distributions, I can draw a picture of this. So we have the middle. I can split this thing up into three in both directions. They represent three standard deviations, left and right. And there's the center. So we can draw a picture, we can put the parameters on there. And so it's a little bit more intuitive, this particular distribution. Let's take a look at an example, then we'll put that information on the board, and then we'll get the computer to work out the defect rate for us using the normal distribution. Let's take a look. Okay, so here we are. The diameter of a fiber optic cable is targeted to be exactly 0.5 of an inch. The specifications stipulate that the cable diameter must be between 0.35 and 0.65. If the data collected indicates we've got a normal distribution with a mean of 0.45 and a standard deviation of 0.1, what percentage of cables produced do not meet the specifications? Okay, so we got the parameters, we got the mean, we got the standard deviation. So let's have a look. We got the mean is 0.45, standard deviation is 0.1. Let's put that information on this diagram. So our normal distribution is centered at 0.45, and then of course each one of these units is going to be a standard deviation increase. So we're going to count up 55, 65, 75, and then we can count down the same, 0.35, 0.25, 0.15. Then what I can do, of course, is drop the tolerances on this thing. So the bottom tolerance is sitting here at 0.35. The top tolerance is sitting there at 0.65. So what we're interested in is the left-hand tail and the right-hand tail. What's the defect rate too small? What's the defect rate too large? And so we can draw this picture. Now normally in SPC XL, what would I use? I'd use the CPK tool to do this because it will draw this picture for me. But we're going to show you to do a formal normal distribution calculation. Let's take a look at the software. Okay, so previously we were looking at discrete distributions. Now we've got a continuous distribution, of course, in the normal. There's a lot of continuous distributions, as you can see. Some of those might be in your business, but the normal is the one we want. Click on normal. You get this window. Mean was 0.45. Standard deviation was 0.1. The lower limit, 0.35. The upper limit, 0.65. And now, of course, it gives you the two tails. So if I look at the top answer there, how much of my data will be less than or equal to 0.35, the bottom tolerance? 15.8%. If I look at the fourth answer, how much of my data will be greater than or equal to 0.65, 2.2%. And of course the bottom answer says, and how much of your data will be between the two tolerances? Now that's almost 82%, 81.8% will be good ones. Okay, let's put that data on the diagram for us. So what did we say? We got 15.8% to the left, we got 2.2% to the right, and in here was 81.8%. They're the good ones. Now, of course, important, this is a prediction. You will notice that we didn't have data in this example, we only had the summary statistics. So we had no chance to make an observational error. We are just predicting from the information we're given that we are going to get 15.8% here, 2.2% here. The CPK diagram would have done that for us and drawn the diagram for us. What the CPK diagram doesn't do though, doesn't split them up left and right tail. So what you would have ended up with is just a straight defect rate, which I think is just 18.1% as a total. So if you actually want to know what's in the left tail, what's in the right tail because of how much they cost you, maybe they cost you different amounts, use the full calculation. If you don't need to know that, the CPK tool will do that. But this is a prediction, not an observation, because often when in probability, when we make observations, that's when we make a gut reaction, and our observational reaction is often wrong, where the prediction result is a better estimate of what's going to happen. If you've got normal data, use the normal distribution, either in your CPK diagrams or in calculating defect rates. Use the normal distribution.